Hi everyone, this is Mrs. GA, and today we're going to be solving exponential and logarithmic equations. Alright, we're going to start by talking about how to solve an exponential equation. So your first step is always going to be to isolate the exponential expression. And once that part is isolated, you're going to take the logarithm of each side. Now, just a little tip that might make it a little easier, try to match the base of your logarithm with the base of your exponential expression, and it will simplify quicker. Then you bring the exponent to the front of the coefficient using the law of logarithms that we talked about in the last lesson, and then finish solving for the variable when necessary. So let's look at two examples together. So we're going to solve for both, and we are going to round to the nearest hundredth, so you will need a calculator for these problems. So in part A, you can see that my exponential expression is already isolated, so that means that I'm ready to move on to step 2, and I'm going to take the logarithm of each side. I'm actually going to choose log base 3 because the base of my exponential expression is 3. So by doing this, you'll see that when we move this to the front, all we have left, so we have x plus 2, and then we have log base 3 of 3, which we know is 1. So this will essentially simplify out. Or you can use that inverse property, and this would just simplify straight to x plus 2. So here I do need to finish solving for my variables, so I'm going to subtract 2 from each side. So log base 3 of 7 minus 2. Now at this point, maybe your calculator can compute something like this. If it can't, we can use that really simple change of base formula and rewrite it with a common log, and then this is what we will plug into our calculator. And here you should get approximately negative 0.23 if you round it correctly. All right, let's try part B together. So remember, the first thing we need to do is isolate our exponential expression, so that would be this part. So I do need to start by dividing both sides by 8. Okay, so now I'm ready to take the natural log of both sides. Again, I picked natural log, so the base of my logarithm matches the base of my exponential expression. And here, if I have the natural log of e to the power of something, it will simplify to simply 3 minus 2x equals the natural log of 4. From here, let's finish solving for x. Natural log of 4, so I do need to subtract 3 and then divide the entire thing by negative 2. And this is what you will plug into your calculator. And here you should get approximately 0.81. And there you have it. So now we're going to try to solve an exponential equation of the quadratic type. So if you look at this, it really looks similar to x squared plus ax squared plus bx plus c, except instead of having x squared, we have e to the x. So a few different ways we can do this. One way is using substitution. So here we can say let x, or let's change the variable, let y equal e to the power of x. So if I make that substitution, what I have left is y squared minus y minus 6 equals 0. This is really easy to solve by factoring, so we can do y minus 3 times y plus 2 equals 0. And then from here, we can say y minus 3 equals 0, y plus 2 equals 0, y equals 3, y equals negative 2, and then we're going to substitute this back in. So we have e to the x equals 3, and e to the x equals negative 2. Now, if you remember what the parent function of e to the x looks like, it's always positive. Plus, we have a positive base raised to a power. It will never be negative. So this actually gives us an extraneous solution. We can't solve from here. But this one we can finish solving. So we can take the natural log of each side. And this will simplify to just x. So x equals the natural log of 3. This is what you'll plug into your calculator to get the decimal approximation of about 1.10. So if you are comfortable factoring this straight like this, you can look at it and say, okay, this is e to the x minus 3 minus e to the x plus 2 equals 0. That's fine. You can go straight from here to here. But if this is a little bit confusing for you, try substituting e to the x with a different variable, and then it's just a nice simple quadratic equation. Just make sure you substitute this back in at the end. Okay, let's try another quadratic type equation. So here we have 3x e to the x plus x squared e to the x. So just like any other problem, you should always look to see if there's any type of GCF you can factor out. And in this case there is. We can actually factor out x e to the x, and then what we have left is 3 plus x, and all of that will equal 0. So from here, we can actually solve this using the zero product property. So I see 3 separate factors, so I can set them each equal to 0 and look at what we have to work with. So here, x equals 0 will be a solution. If you look at this, e to the x equals 0, well, we know it's impossible to take a positive base, raise it to a power, and get 0, so this is extraneous. So we ignore that factor, and then this gives us x equals negative 3. So again, try not to get overwhelmed when you see e to the x in this equation. Just factor it out just like any other problem and see what you have to work with. All right, go ahead and pause the video and see if you can give these 2 problems a try. We'll check our answers in just a few seconds. All right, go ahead and check your work here. So remember, isolate. Here I took log base 3 of both sides, and then you do have to finish solving for x. If your calculator can't compute log base 3 of 5, use that change of base formula, and you should get this as your decimal approximation. For part B, either you can go straight to the factors or feel free to use substitution. If you are a little bit confused when you see something that looks like this, either way you should get the factors e to the x minus 5 times e to the x plus 2. This gives us an extraneous solution, and this, if you finish solving, gives us approximately 1.61. All right, so now we're going to move on to solving logarithmic equations. So the process is very similar. First, we're going to start by isolating the logarithm. However, in order to do this, you may need to combine your logarithms first. So if you have a sum or difference of logarithms on the same side of the equation, combine them into a single logarithm first. Then, once you have isolated your logarithmic term, you're going to rewrite the equation in exponential form, and then finish solving for your variable when necessary. All right, let's give these 2 a try together. So here I'm going to start by isolating our variable. So we'll start by subtracting 4 from each side, and then divide by 3. So our logarithmic term is completely isolated. So now at this point, I'm going to rewrite this as an exponential equation. Remember, common logs have a base of 10. So 10 to the power of 4 equals 2x. So x will equal 10 to the power of 4 divided by 2. So you get x equals 5,000. Now for any logarithmic equation, before you box your answer, it's really important that you check to make sure your answer is valid, because we know that logarithms have restrictions. Here we have base 10, so we're taking 10, raising it to a power. We know that this value must be positive. So you do need to substitute your value for x into your logarithm to make sure that it stays positive. So we'll do a really quick check. This one's pretty easy to check. This gives us the log of 2 times 5,000, which is 10,000. So that's totally valid. So remember, this value needs to remain positive. So as long as your x value doesn't turn this negative, it is a valid answer. Now let's look at part B. So here you can see that I have two separate logarithms. So our first step is going to be to combine these into a single logarithm using those laws we talked about in the last lesson. So if you see a sum of two logarithms, we can turn it into a single log of a product. So I'm going to multiply x plus 2 and x minus 1. Here, let's multiply that out before we rewrite it. So we get x squared plus x minus 2, and then equals 1. Again, common logs have a base of 10. So this becomes 10 to the first power equals x squared plus x minus 2. And now we have a quadratic equation. So let's set our equation equal to 0. This we can solve by factoring. And here, this gives us two x values. We get x equals -4 and x equals 3. So let's check both of those. So let's check x equals 3. So that would give us the log of 5 plus the log of 2. This is totally valid because both of our logarithms have a positive value here. So this value works. And now let's check x equals -4. So just by substituting it into that first equation, we get the log of -2. This value is undefined. So therefore, x equals -4 was an extraneous solution. So our only solution is x equals 3. So just remember, for these problems, you do need to check to make sure that this value remains positive for your given x values. All right, go ahead and pause this video and give these two a try on your own. We will check your answers in just a few seconds. Okay, here you can see that by simply rewriting it as an exponential equation, we get 8 equals 22 minus x. Very easy to solve. Please make sure you double checked. Here, if you substitute x equals 14, you get log base 2 of 8, which is completely valid. For part B, after you condense your logarithms and rewrite, you get a quadratic equation that gives you two solutions. Now when you check, x equals 2 is valid. However, x equals -9 gives you undefined expression, so therefore our only solution should be x equals 2. All right, so now we're going to talk about a really common application of a exponential function, and that's the compound interest formula. So this formula helps you determine how much money you have after a given time from an account that generates interest. So a few things to know about this formula. P is called the principal amount. So that's how much money you start with in the account. And then it's times 1 plus R over N. R being the annual interest rate as a decimal. It's really important it's written as a decimal. And N is the number of times the interest is compounded each year. So essentially that's how many times the bank goes into your account, sees how much you have, and pays you interest on it. And then all of this you raise to the power of NT, and we already talked about NT is the number of years. So you can compound your interest annually, twice a year, you could do it quarterly, you could do it monthly, daily, or you can do what's called continuous compounding. So this actually has a slightly different formula. So notice here we have a equals p times e to the power of rt. So base e helps us generate this continuous compounding interest, and essentially that would be like if every single second and millisecond of the day you were getting paid interest for the money that you have. So this is the formula you can use for that. So we're going to be solving for different parts of the formula, but now we know how to solve any exponential equation, so it should be pretty easy for us to do. All right, let's start with this first example. This says a sum of $5,000 is invested at an interest rate of 5% a year. So here they're asking us to find the time required for the money to double if the interest rate is compounded according to the following method. So we're going to do one calculation for a semi-annual compounding account, meaning it's compounded twice a year, and one for continuous. So let's write out the information, or let's start by writing out the formula, and then we'll see what information we have and what we need to solve for. So here we have a equals p times 1 plus r over n to the power of nt. So what we know, well, we know that the principal is 5,000. That's how much that we started with. And we know that we're calculating the time it takes for the money to double. So that means the amount in our account after that time should be double 5,000, which is 10,000. Other things we know that our r value in this case is 0.05. So that's 5% written as a decimal. And we know that n equals 2 because it's compounded twice per year. And here we are trying to solve for t. So let's plug in the information we know into our formula. So 10,000 equals 5,000 times 1 plus 0.05 over 2 to the power of 2t. And here you can see that we are just solving an exponential equation. So just like we've been doing, we want to start by isolating our exponential expression. So I'm going to divide both sides by 5,000. And let's simplify what we have inside the parentheses. So this will become 1.025 to the power of 2t. So now we can finish solving by taking the log of both sides. Here we don't really want to do log base 1.025, so let's just do the common log of both sides. Okay, now I'm going to take my exponent and move it out front. So 2t times the log of 1.025. And then to finish solving for t, I can divide both sides by 2 times the log of 1.025. So we end up with log of 2 divided by 2 log of 1.025. And then if we take this and plug it into our calculator, we get approximately 14.04. So our final answer would be 14.04 years. And there you have it. So again, this is just a matter of plugging in your given information into the formula. The rest is just solving an exponential equation, just like we've been doing for the entire video. All right, now let's try the same information, except the only thing that's different is going to be that it's compounded continuously, which means that we actually use that second formula, which is a equals p times e to the rt. So again, we still have the same p value. We still have the same a value. We still have r. Here, this formula doesn't require n because that's covered with the base e, and we're still solving for t. So let's substitute what we know. Times e to the 0.05 t. Let's isolate our exponential expression, which would be this part. So let's divide both sides by 5,000. Here, let's take the natural log of each side, so we can match with base e. So we have natural log of 2 equals the natural log of e to the 0.05t. Here, I have base e, so it will simplify to simply 0.05t. And then to finish solving for t, we can divide both sides by 0.05. So from here, it's simply a matter of plugging it into your calculator for a decimal approximation, and this gives you 13.86. So it would take us 13.86 years to double our money if we had an account that compounded our interest continuously. So you can see that the more often you compound your interest, the quicker you can double your money. All right, that is all for today's video. Thank you so much for watching.